So let's go ahead and practice the ideas of calculating some Riemann sums to estimate areas under curves by looking at example 1 and the associated parts. So let's see what we have here. Let's suppose that A is the area of the region that lies above the x-axis, but under the graph of f of x equals x squared, on the interval where x goes from 0 up to 2. All right, so I'm going to start by at least sketching out here a rough picture of what we're dealing with. Notice that I only need to go from 0 to 2 in my picture. And so when I sketch out my graph here of y equals x squared, I really only need to kind of care about this right side. So you can see I'm not really drawing much of the left side. So if I was to go from 0 to 2, let's say it looks like this. So I can see that what I'm really looking for here in this picture is to find the area under this curve, and that would be this specific area, all of this space here in red. This is what I'm attempting to find. I want that area. Now again, that's not a nice geometric shape, so I can't find it directly, and this of course then is why we need to use an approximation technique like a Riemann sum. So to help try to approximate this, let's take a look at the following. I'm going to go ahead and try to use here a left Riemann sum with 4 rectangles. Okay, so let's start with the idea that we have 4 rectangles. The number of rectangles that I have is going to definitely affect how wide each rectangle can be. So let's start by calculating the width of our rectangles. Remember that our width can be represented by the symbol delta x, since this will tell us kind of how far to move in the x direction to find the width of a rectangle. And remember that we stated in the last video that to find that, I would need to know how long my interval is, and then how many pieces I'm essentially going to chop it up into. So in this case, my interval is 2 minus 0 units long, and I want to chop that up into 4 equally sized pieces. So overall, I see that each rectangle can be 2/4 or 1/2 of a unit wide. So let's go ahead and see if we can try to figure out what that would look like here in the picture. If this is where the value of 1 is, then I can easily identify where 1/2 is and where 3/2 or 1.5 happens to be. And so now I can easily see each rectangle occurring in here. Right? This is kind of the bottom edge of each of my rectangles, and I can see I've constructed 4 of them. Now if this is supposed to be a left Riemann sum, I should go to each rectangle, at least the base of it, and I should start by going to the left side of that interval. So take a look here at the interval from 3/2 to 2. Notice here I'm going to start at the left-hand side, and I'm going to use this side to determine the height of the rectangle. I'm going to go all the way straight up until I hit my function, and then I can see that I have 2 edges of a rectangle. So I should be able to kind of create the rest of the rectangle right there. And I'm going to do this for each individual interval. I'm going to go from the left edge, up and hit the function, and then go straight over. And this is my next rectangle. Over here, I'm going to start at the left edge, go up, and there's another rectangle. Now this side, or this last rectangle over here, is kind of interesting, because if I start at its left edge, and then I say go up until I hit the function, notice that nothing really happens there, right? Like I'm already at the function, so I can't really go up at all. So this rectangle is going to be really boring because its height, how tall it is going to be height 0, which means that it's not really going to generate any area. So I can see all these kind of white, almost triangular pieces in this picture are going to be bits of area from the original region that I'm not going to be accounting for. And so very clearly my guess here is going to be an underestimate. But let's figure out what it actually is going to, what this estimate is actually going to be. So I'll start here by doing my calculation and saying that the total area under the curve is approximated, it's roughly equal to doing the following. Okay, so let's see. I'm going to do all my heights times my widths. So the height of my first rectangle, I know that I would find by plugging 0 into my function and then multiplying by 1/2. My next rectangle, its height, would be found by plugging 1/2 into my function, and then its width is also 1/2. Same thing for my third rectangle, and finally for my fourth rectangle. So if I can just go ahead and evaluate each of these f of values, like f of 0, f of a half, so on and so forth, and again, keeping in mind that my function up here is just x squared, then I should be able to crunch this out into a final value. One thing that I'll note right away, though, again, is that since my width is always in common between each rectangle, I can factor it out and then simplify what I have left. So notice here that f of 0 is just going to be 0. F of 1/2 is going to be 1/2 squared, or 1/4. 3/2 plugged in here is going to be 9/4. And if I plug 2 in here, I'm going to, oh, wait, did I do this correctly? I think I messed up one of my heights here. Let's double check. My apologies. Let's see, so here I had f, I was looking at my third rectangle. Oh yeah, it looks like I skipped something. My third rectangle's height would have been found by doing f of 1. And my fourth rectangle would have been by doing f of 3/2. So I don't get 9/4 here because I'm instead supposed to be computing f of 1. And that's, again, really easy. F of 1 is 1. Now f of 3/2 would be my 9/4, and that's going to look like this. So notice that I could simplify this just a little bit more. Let's see, I'm going to have 10/4 in there. I think this is going to be a total of 14/4. Or if I was to compute this, let's see, this would be the same thing as 14/8. Or you could probably approximate or get this as a decimal value at 3.75. You could double check me on that, but I think that's actually going to be good. Oh, sorry, not 3.75. There's no way that that's right. That would be a value of 1.75, excuse me. So I can clearly see here, though, that this is going to be an underestimate. And so I'll even mark that here. This here is an underestimate. But hopefully making this calculation and setting this up is fairly simplistic. Notice that all I'm doing is identifying that if I'm working with the left Riemann sum, I start with the left side of each interval, go up and hit the function. If I was doing a right Riemann sum, I would do the same thing, just starting with the right side. So let's go ahead and take a look at part B, where I'm actually going to be asked to do a right Riemann sum. We're still going to be asked to work with 4 rectangles. And so as I start to draw my picture, I'll recognize that it's almost going to be identical to the picture that we just were working with. So let's suppose again that I have 2 maybe sitting out right here. So if I'm going to be working with 4 rectangles again, I can kind of know already where they're going to be. I'm going to have a rectangle that stretches from 0 to 1/2, just like up above, 1/2 to 1, 1 to 3/2, and 3/2 to 2. So again, the width here hasn't changed at all. The width here, or my value of delta x, is still going to be length of my interval over number of rectangles. It's still 1/2. Now I'm going to ask you to go ahead really quickly and pause the video here. See if you can actually go ahead and sketch out what the rectangles would look like. Just make sure you're going to start from the right edge of each one of these intervals and go up and hit the function, and then create your rectangle. I can definitely tell you that this time you will certainly not get a picture that shows that we will be underestimating the area. But go ahead, pause the video, see if you can work through this and get down to a final approximation. And then, if you unpause the video, you'll see me work through this solution and also go ahead and tackle part C. All right, so hopefully you did actually go through and try this out. Here's what my rectangle should look like. If I'm going to the right side of each interval and going up, my first rectangle should look like this. My second rectangle should go up from 1 and come over. My third rectangle should go up from 3/2. Notice I'm going all the way up from the right side until I hit the function. And so I'm going to get rectangles that look like this. And so clearly here I'm going to be getting an overestimate. So we could now start by saying that my area overall is going to be roughly equal to, and I'm going to jump into my calculation here. Obviously there's going to be a 1/2 that's in common for the width of each of these, but now I can start to figure out the heights of each of my rectangles. The first rectangle would have a height by going to f and plugging in 1/2. The second rectangle would have a height determined by f of 1. The third rectangle would have a height determined by f of 3/2, and the last one would be determined by f of 2. So if I was to go to my function x² and plug all these in, I'm going to get a value of 1/4 plus 1 plus 9/4, and finally plus 4. So overall, I could see here that, let's see, this is going to be the same thing as 1/2 times, let's see, I could write this as something like 0.25 plus 1 plus, what would this be? That's like 2.25 and then plus a 4. So overall, I can see here that this is going to be half of, what's that going to be, 7.5 in there? So if I take 7.5 and I chop it in half, I'm going to get a value of 3.75. So again, since my picture here is grabbing way more area in blue than there was area under the curve, I know automatically that this value is an overestimate. So I can kind of see then that, wait, I provided an underestimate of 1.75 back in part A. I provided an overestimate of 3.75 in part B. So the real area must be somewhere in between those, right? Somewhere bigger than 1.75, but smaller than 3.75. And so we're slowly starting to whittle this down. So hopefully you were able to get to an answer like this. And let's go ahead now and take a look at part C and see how things would change if I was going to be working with a midpoint Riemann sum. And even still, what would happen if the number of rectangles I was going to change. Now, over here, I can see that I'm going to, again, still need to draw out my picture to help me at least try to think through the process of what's going on. So let's suppose that, again, 2 is over here, and here's 0, so here's 1. And this time, I'm going to start by calculating my width, just like I have in the past, still calculating delta x. I'm still going to have an interval of length 2, but now if I want to cram 8 rectangles in here, I'll notice that, each one cannot be very, very long. It can only be a quarter wide. So notice that if this is a half, then I'm going to have to chop that half in half to get quarters. And so if this is 3/2, then notice I'm going to have rectangles that are going to be associated with these 1, 2, 3, 4, 5, 6, 7, 8 different intervals here. Okay, so if I wanted to calculate my area, I would notice that the total area here is roughly the same as 1/4, which would be multiplied to each one of the heights. And so I'll just kind of preemptively factor it out. But how do I find all of these heights? Like, I can start to draw the picture at least, right? Like, let's start over here. What I would do if I'm dealing with a midpoint Riemann sum is I would say, okay, I know that like my first interval here goes from 0 to 1/4, because it's supposed to be only a quarter wide. And so if I went from that distance, or if that's the length there, then I'm going to grab a value that's right smack dab in between, and then I'm going to go up until I hit the function, and then I'll kind of draw a rectangle that goes over. So I establish the height, and now there's my little rectangle. I would do the same thing with each interval. I'd say go to the middle of the interval, then go up, hit the function, and kind of cap off the top of my rectangle. I'll draw that out here for each one of these. Okay, so let's see what this would look like. So I'm going to get an interval that or a rectangle that goes like this. Here I'm going to go up from the middle. Each one of these I'm just going straight up from roughly where the middle is, trying to keep track of roughly where that's going to land me. Okay, so again, going from the middle all the way up would land me maybe somewhere around here. Going all the way up from the middle lands me somewhere maybe around here. So again, this is just a quick rough sketch, but you can see that I'm going to get rectangles here that are going to be approximating my region in a way that's probably going to make it difficult to tell if I have an overestimate or an underestimate. And you can kind of see that by maybe, say, taking a look at one of the rectangles that I have over here. One of the taller ones at the right. Like, take a look at this last rectangle. I can see that in this space, right in here, I'm clearly overshooting the amount of area that I need. However, on the other side, you can see there's kind of like this little portion here where I'm going to be underestimating. And so I'm kind of simultaneously over and underestimating, but I kind of don't know which one is being worse in that sense. So it's going to be really difficult to tell if this is an over or an underestimate. But let's go ahead and take a look here to figure out how I would determine where each of these midpoints is located. Well, here's what I like to do to try to to try to determine this really, really easily. First, I can figure out this first midpoint. I'll draw it here in red. And I know that this first midpoint right here is just going to be in between these two values. That is, it's kind of like the average of 0 and 1/4. So if I wanted to average those out, I would just do 0 plus 1/4, and I could chop that in half. That's finding the midpoint of those two. So that would give me a value here of 1/8. So I would know that my first rectangle's height would actually just be f of 1/8. That's how I would find it. Now, this is a little bit tedious to imagine doing for every other possible midpoint that's going to be in here, right? Could you imagine having to compute an average or find the midpoint for each individual piece as I move down the line? That would be so annoying. I have 7 more of these to find, which means I'd have to know the endpoints of each individual interval. It would be a whole ordeal. But here's something that's really, really interesting to note. First off, again, how wide was each rectangle? Well, it was a 1/4 wide, right? So how wide is it from the midpoint to, say, the end of the first interval? Wouldn't that just be like half of a 1/4, or again, 1/8? So this distance right here from the midpoint to the edge is 1/8. And then how far of a distance is it from this edge to the next midpoint? Wouldn't that be another 1/8? So this is 1/8 and 1/8, or 2/8, or this is 1/4. It's actually still one full width of a rectangle to move from midpoint to the next midpoint. And I should note here that that's the same thing then as saying 1/4 is the same as 2/8. So take a look at what I'm going to do here to quickly generate all of the rest of my midpoints. I know to jump to the next midpoint, I have to move over 1/4, or 2/8. So 1/8 moved over 2/8 would be 3/8. Well, what about if I wanted to go to the next one? Just move over another 2/8. So that would be 5/8. And you can see I could start to write these out really fast. Then I go 7/8. I'm just adding 2 more eighths every time. And then I'm going to go to 9/8. And I know that I should only have 8 of these because I'm going to have 8 total rectangles. So I'm really going to have to cram these in. I'm going to go to 11/8, and then 13/8, and then I'm going to have to keep going one more time, 15/8. Right? Notice there I have 1, 2, 3, 4, 5, 6, 7, 8 total rectangles, and I'm good to go. Now, I can go ahead here and actually multiply the 1/4 times all of this if I'm able to just quickly evaluate what each of these things is going to be. Now, this is actually really easy because, again, I'm working with the function of x squared. So notice I'm going to get something like 1/64. Squaring here, I'm going to get 9/64, 25/64, 49/64. Right, I'm just squaring top and bottom here. So let's see, 81/64, 121/64. Let's see, 13 squared should be 169/64, and 15 squared is 225/64. Now you can double check my numbers on this, but I think if you were to add all of this stuff together, you would end up with a grand total of 680/64 here. And so if you divided that by 4, you would end up with a total of 85/32 if you fully reduced everything. Now, this, of course, is going to give you some decimal approximation for the total area that's going to be in here. But for the moment, this is completely sufficient. I've used this midpoint idea, which is a little bit more complicated to get through, to again find an approximation. However, we should note again, it's kind of difficult to tell if this might be an overestimate or an underestimate. But chances are it's somewhere in between what we got for parts B and part A. And so it might provide us, at least for the moment, with the best possible approximation thus far. Now, in the videos to come, we'll take a look at some other interesting ideas related to these ideas of Riemann sums and how exactly to compute them, and some other things we have to be careful of. And we'll again talk about those in the videos to come.